Hello, my name is Justin Liu, and here's my project presentation. The system I'm working on is a 2D inverted pendulum on a cart, which has been heavily simplified. This cart is constrained to move only in the x direction. This pendulum rod is massless but infinitely rigid. And the system is inherently unstable. Any disturbance force, W1, will just knock the pendulum over. So the objective will be to keep the pendulum upright, using only this controller force U, which acts only on the cart. From the model, I just used a standard GK framework with process noise and sensor noise. I constructed free body diagrams. I used the summation of forces and torques, and I created equations for theta double dot and x double dot. I used small angle approximation to linearize everything. And here are my states down below. We have pendulum angle, its velocity. And we have cart position and its velocity. And we have this equation right here that pops out. This is just the dynamics of the system. For exogenous outputs, these are the things we want to minimize. Z1 I chose as pendulum angle. This is the thing we want to keep at 0. And then Z2, this framework chose the controller output because we want to keep this at a reasonable level because this is the force we'll be exerting on the cart. For our outputs to the controller, this is what the controller sees from the state. I arbitrarily decided that the controller can only see the pendulum angle and the cart position right here. And we can't forget about sensor noise, which corrupts the signal right here. That's reflected by this column of 1s and this W2 right here. For autonomous stability, we already know the system is unstable, but we can still solve this LMI and find that the LMI just returns an infeasible result for P, so the system is not stable. For controllability, if the system is controllable, this LMI at the bottom will return a feasible result for X, and it does, so that means the system is controllable, and since the system is controllable, it is also stabilizable. But as you can see over here, for my plant and controller, my D2 is equal to 0, so that means the system is well posed, so that means it automatically gains stabilizability and I believe it's called detectability. But in any case, I opted to go for the optimal H-infinity output feedback controller, and here is my interconnection right here. And here is my theorem, or the theorem states that we have to solve this LMI to find the most optimal controller. And to solve the LMI, we have to minimize gamma. When we plug this into CVX, we get these matrices right here. And we plug those matrices into this equation right here. And you'll notice that the K2s are gone because D22 is equal to 0. So that means Q is equal to I, identity. And that means we could just plug in the controller values right here. X2 and Y2 must still satisfy this condition right here. I just use these values right here. For the simulations, up in the top right, these are the constants I chose for my variables. And here are my results. So yellow is the sensor noise, has no real unit. Orange is my process noise, it has newtons, it's in newtons. I have a sinusoid signal on the left and a square signal on the right. And in blue is my pendulum angle, stays pretty constant at 0. And on the bottom is my controller output. It has to work 5 times as hard because it's 5 times as heavy as the pendulum. So yeah, if you zoom into the pendulum angle, you can see we have a peak of around 0.005 radians for my sinusoid input, and we have a peak of 0.007 radians for my square signal. That's pretty good. For limited state, for full state, I decided to do a test. What would happen if I gave the controller full access to the state? That's reflected by this identity matrix right here. But I also wanted to still corrupt it with the sensor noise right here. So the left side is my original system, and the right side is my full state system. The first thing you'll notice is that the pendulum angle, it's a lot worse than the one for limited states. So it's kind of strange. And the second thing you'll notice is that my controller output is a lot more susceptible to noise compared to this controller output. And also, this peak is around 15, 20, whereas this peak is around 5. So that's very strange. And I think it might have something to do with my sensor noise. This column of 1s might not be correct. I think that the coefficients for position, these two, and for velocity, these two, I think they should be different. But I'm not quite sure what they should be. It's something for the future. So in conclusion, my controller works very well. Here's my uncontrolled system. Uncontrolled system on the left, no controller output. System just goes crazy. But once I apply my controller output, my pendulum angle becomes stabilized at 0. So some things to do in the future I'd like to do. I'd like to make my system model more realistic. So I have the rod have mass, and it'll be a little bit, the state space representation will be a little bit more complex, but it'll be more realistic. I'd also like to figure out, get to the bottom of what's happening with this clump of ones right here. Why do it, when I send full state to the controller, it performs worse than when I send, only 2 states to the controller. So yeah, thank you very much.